involved in unsupervised learning. Please.
Okay, thanks. Thanks for coming. So this is joint work with Elad, which is going to appear in NIPS just next week. So we have a joint framework and convex fixation for unsupervised learning. So what is unsupervised learning? So if you Google and Wikipedia will tell you unsupervised learning is the machine learning task of inferring a function to describe hidden structure from unlabeled data. I guess the important thing is that we only have unlabeled data. It's a restriction, but it's also a powerful thing because we can assume, in some sense, we have infinite unlabeled data. Just to convince you, this Wikipedia text corpus, right, as a collection of documents. This is a public data set with 6 billion tokens, basically 6 billion words. And there's another bigger one, which is called Common Crawl data set. This is basically kind of like a collection of all the documents, online, and it consists of 840 billion tokens. On the other hand, just to compare with this, the labeled data set, right? So this is, I'm going to use the Stanford question answering data set as an example. This is data set with documents, questions, and the answers are considered as labels, and there are only 100,000 question answer pairs. And this is the largest one. It was just released this June by the group of Persilian. So, and it already gives a lot of excitations. There are a lot of people working on it. However, you can see that it's still very small compared to Wikipedia. And there's another data set which is machine translation. This is probably the biggest one in natural language processing, and it only contains 300 million English words and 350 million French words. So, and for images, the same thing happens, right? So on one side, we have basically all images on the web, right? I'm not sure how large it is, but at least several hundred millions, at least. And on the other side, the largest data set in computer vision nowadays is this 1.2 million examples in ImageNet. So presumably we have much more information, when we do unsupervised learning without the label. However, the challenge is, how do you do it without the label? So, and there are successful examples of using this super, big data set. So we can train word embeddings, we know how to train word embeddings from this Wikipedia data set or the Common Crawl data set. And this cannot be done, at least not yet, by using the small label data set by any means. So, and also this word embeddings, you may wonder, what it's good for. They can be used for many other actually supervised tasks because you take a document and you embed it in Euclidean space, and that's your new feature, and you use that for the supervised task. So this slide is just to trying to convince you that unsupervised learning could be powerful. Okay, so now let's read the second sentence on Wikipedia about unsupervised learning. So since the examples given to the learner are unlabeled, there is no error or reward signal to evaluate a potential solution. So this sounds a little bit, problematic, fishy, right? Because there's no even way a good way to evaluate your potential solution, and how do you compare, one solution with the other? And this is exactly what we want to address in this talk, right? We have an definition for evaluating the solution. So we have a definition for unsupervised learning where we can evaluate a solution and compare them. And we also have 2 convex relaxations for 2 examples of unsupervised learning problems. Okay, so just to motivate a little bit more about this unified framework about unsupervised learning. So when this is a course at Stanford, CS 229, taught by John Ducci on machine learning, and we can see that on one side, for unsupervised learning there are 5 classes: clustering, k-means, PCA. On the other side, for supervised learning there are 7 classes. And among them, there are 3 classes about learning theory. However, for the unsupervised learning part, it's just like a different questions and without kind of a unified theory. So I guess this is another picture just to convey this idea. For unsupervised learning, we have all of these different questions with somewhat theory. Some kind of different measure of quality of solutions for different problems. But for supervised learning, we do have a unified theory, packed learning. To kind of connect all of these together. Okay, so just before talking about unsupervised learning, let's just remind ourselves about the framework, the pike learning, the statistical statistical learning theory. So in statistical learning theory, you want to learn a function that maps data to the prediction. So often, the goal or the way to measure the quality of the solution is to measure how well the prediction or our prediction h of x matches the ground truth label y. According to the error function, so you can choose some error function L, and this is a function of the prediction and the true label. For example, L2 loss between the difference. So after we define this error function, on one example we can define it for all of the examples, in the sense that we can define the expectation over the distribution of the data. No, the expectation of the error over the distribution of the data. And the goal is that we have some hypothesis class, right, which contains a set of possible functions, and if this hypothesis class is learnable, if and only if if exists an algorithm after seeing polynomial examples with high probability, this algorithm will find a solution function h such that the error of this function is smaller than the minimum error plus some approximation error. So this is a kind of a clean framework where you can evaluate your solution using this error function, and you compare it with the best solution among the hypothesis class. Okay, so this is the classical statistical learning theory, and we want to generalize this for unsupervised learning by defining a reward function for evaluating the potential solution. So kind of the rationale here is that we want to learn a representation of the data which can be used for solving any future supervised task. And let me elaborate on this. So here, instead of learning a function that maps the data to the prediction, we are learning a function that maps the data to the representation of the data, a new representation of the data. And we have two criteria that evaluate this, the quality of this function. So one is compression. We want the representation has explicitly succinct representation. Say hx has low dimension in 0, 1 bit, and so this will ensure that we have a low sample complexity for future supervised tasks. So maybe let me elaborate on this. So by solving future supervised tasks, I mean that we take the representation instead of the data. So this is our new data, and we learn the mapping from the representation to the prediction. That's what I mean by solving future supervised task. And we can see that if the representation is of low dimension, then the future supervised task has better sample complexity, just because the dimension is lower. Roughly speaking. So on the other hand, we also if it is just one such a thing, then it's easy. You just compress it to anything you want. However, we also want to not lose too much information in this representation. We want to have a decoder G such that if you apply this decoding function after this encoding function, then we can reconstruct the original data approximately under some metric.
There is an old notion of compression and reconstruction of Lidstone and Varmont, I guess.
Yes.
You are generalizing it, or you mention it?
I will compare it just in a moment. Maybe, yeah.
Are you going to talk more about what metric and why, or that seems to be...
Yeah, next slide. Yeah. Yeah. So let me just motivate why we want to have construction. If you have reconstruction, this will maintain the necessary information for future supervised task. That's kind of the rationale. Okay, let's make this okay. What's the difference from the coding theory or like information theory? So first of all, we have a reconstruction matrix of your choice. So you can choose this matrix. Maybe you can choose L2 or L1. It doesn't have to be like for example, entropy, or doesn't have to be like you don't really want to reconstruct, for example, every bit of our original data. And then this could be lossy, right? You are allowed to lose some information that is not useful. And this is characterized by the choice of the matrix, right? If you choose some matrix, then it's more likely that you can maintain some kind of information. If you choose another matrix, maybe you're going to maintain some other kind of information. And another feature, the difference is that we want to have a comparative result, a comparative framework. We want to compare with the hypothesis class of encoder and decoder, but not compare to all possible encoder and decoder. By this, what I mean is that we have a hypothesis class H, which is a subset of all possible decoders and encoders. And we have the constraint, compression constraint. We say, for simplicity, let's say we want the compression, to be in dimension k, in Euclidean space. And we have some reconstruction, and the error is defined as the expected loss on every example, right? There's a loss function, which is the metric. And formally, we say a hypothesis class H is learnable if an algorithm, after seeing polynomial examples with high probability, finds an encoder and decoder such that the error is comparable to the best error among this, the best error of the decoders and encoders among this hypothesis class.
Sorry, the first point is not really a difference with coding. A red distortion theory doesn't ask you to pick your metric. You can choose whatever metric you want.
Okay.
Because that's the entire field of red distortion theory. You can do M2, you can do mean, you can do other things.
I see.
This is true.
The second one would be just constraining your encoder and decoder. Also, like encoding, if you do a message padding or if you do whatever structural, there's also a whole sub-branch of types of encoder and decoders that are constrained.
I see.
But you'll see the algorithmic part. So if you don't do something comparative and you restrict yourself to learning within the class, computation is very hard many times. So the only way you can overcome it is by learning encoder, which is not in your class. You will see now.
Yeah. Okay, so we are going to have two examples under this framework. One is the polynomial time learning of algebraic manifolds, and another one is a polynomial time algorithm for diction learning. Let's start with the first one. So just before going to that, let's take a step back and see why PCA can be casted into our framework. So principal component analysis, the standard definition is that we have some data, we have some, we want to find a low rank matrix, like a low rank projection that maps the data to, some projected data, so some low rank subspace, and they want to maintain as much mass as possible compared to, the original data. So this is what PCA is going to do, and viewed in our definitions, what we're going to have is that we have an encoding function H, and this H is a linear transformation that maps dimension D to dimension K, and the decoding function is just the pseudo inverse times the encoding, and you see that if R is the R before is just the A pseudo inverse times A, that's the projection to the subspace of the columns of A, and so we just replace R by A pseudo inverse times A, and we get the same thing. This is nothing deep. It's just a change of language, and it turns out that this can be computed in polynomial time just because you can solve this in polynomial time. Of course, you cannot solve the real expectation version. You have to replace the expectation by empirical estimate. However, even you replace by empirical estimate, this is a convex. This is an eigenvector problem, and you can solve it in polynomial time. And so this is how we interpret PCA in our framework. And now let's look at something a bit more complicated. So before we said that, okay, the data is close to some low rank subspace. And now we consider this case when the data to the tensor power 2 resides approximately on a low rank subspace in dimension D square. So just concretely, if let's let the rows of A, so A is a matrix of dimension K times D square, and the rows of A be the basis of the subspace, and let the C to contain the rows that are complement to the subspace. Then, this is kind of this scenario is equivalent to the scenario that all of your data resides close to some algebraic manifold of degree 2. Basically x to the tensor power 2 will vanish on the complement subspace. So that's why we call it the algebraic manifold. And what are the encoders and decoders for this problem? So the encoders naturally is just you want to encode this by the projection, the linear transformation. The encoders is a little bit subtle, right? So the first thing, okay, similar to PCA, what you want to do is that you take the pseudo inverse of A and multiply it with the encoding, and then we take this Vmax. Vmax is the largest eigenvector of S. So, and to see this, we have A times x to the tensor power 2. This is the encoding, and we multiply this by the pseudo inverse. And because X is, say, close to the subspace, A pseudo inverse A is just projection to the subspace. That's why this three things together is approximately the x to the tensor power 2 itself. And if we take the top eigenvector, we shape this x to the tensor power 2 as a matrix, and then we take the top eigenvector, we expect to have x back. So this is the decoder that we're going to consider. And let me just mention that this is related to kernel PCA. In kernel PCA, the only difference is that instead of requiring the reconstruction of x in kernel PCA, we only require to reconstruct. In addition to reconstruct x to the tensor power 2. So it's a stronger requirement. Okay.
If you reconstruct x, why won't you reconstruct x tensor 2 also? Like the error blows up.
Oh, sorry. Yeah. Sure, but I think it's maybe I should say it's more natural to reconstruct x tensor 2 first, right? Because you don't have to do this Vmax. And of course, the vice versa is also true, right? If you can reconstruct x to the tensor power 2, you can approximate. Yeah.
So then they are the same up to some translation of error?
Yes, but it also depends on how do you define the error. For example, if you want to reconstruct x to the tensor power 2 in Euclidean norm, that's an overkill. Because you only need to reconstruct x to the tensor power 2 in spectral norm. Yeah, I think I will talk a little bit about it in a moment. Okay, so our theorem is that we call it this. By the way, we call it spectral autoencoder. Spectral autoencoder is learnable with encoding length k to the 4 over epsilon to the 4 for error epsilon. So we see that we lose something on the encoding length, right? Ideally, we want to have encoding length k, and we lose a polynomial factor on that, and also we have some polynomial dependency on the error epsilon.
Maybe it's good to remark, so it is hard to learn properly, like NP-hard. So back to Emmanuel's question, right? If you just want to learn it within the class, it will be NP-hard to learn. We don't allow some relaxation.
So I guess, just to continue on what Elad remarked. So, if you do the straightforward optimization, what you can do is that, okay, I'm going to minimize, this is my error, right? This is my reconstruction Vmax of these whole things. Minus x, this is the reconstruction error. And I'm just going to optimize over the matrix A. And you can see that this sounds like quite complicated, right? There is this eigenvector operation. It's not even a smooth function or a Lipschitz function. It is a Lipschitz function, but it's not. It doesn't have even second order derivative. So what we are going to do is that we are going to take a convex Vexation, and so here we replace R. We replace A pseudo inverse times A by a matrix R, and R has to be low rank. We cannot really say R is low rank. We say R has nuclear norm less than K, the Schrödinger 1 norm. And also we remove this Vmax because we have this the Vmax of the difference between the top eigenvector of two matrices are bounded by the spectral norm of the difference of these two matrices. So that's why we also have another relaxation in this sense. We remove the Vmax and we only measure the spectral norm of the original matrix. And going back to Pravash's question, so if we do kernel PCA, then this will be Fubini norm because you want to reconstruct x to the tensor power 2 with Fubini norm. And again, just the intended solution is R is equals to A pseudo inverse times A.
Can you explain why this is a good loss? What use are you going to make of it?
I'm going to use this for optimization.
Optimization what?
For finding, I guess maybe, let me just finish this and I'll go back to it. So you can optimize this because, one reason I want to use this is that now it becomes a convex relaxation. It's a convex loss. you know, you can do, I mean, any probably convex relaxation methods, but we really need to use a non-smooth projection-free algorithm. The reason is that we don't just want to have a matrix R, because if the matrix R is dense, then it's not of very good use for us. We really want a low-rank matrix R, which is factorizable into A times A pseudo-inverse times A. And this projection-free algorithm can give us a low-rank solution R. The idea is that, you know, this algorithm every time only have a rank 1 update, and if this algorithm converges fast enough, then you're going to have a low-rank solution. That's one reason why we want to use this convex solution. I'm not sure that
you said because you can compute it. That's what you're saying.
We can compute it and also compute. We can also compute a low-rank solution.
No, I guess the next question is, why is operator norm a good loss to consider?
Is that your question?
Yeah, that's my question.
Oh, yes.
Like,
So,
you know, hinge loss is a good loss, right? It makes sense. Why does it make sense?
oh, so because it's you know, it depends on, I mean, compared to kernel PCA, the reason this is a good loss is it requires less. So it's less stringent in the sense that you know, you might be able to find a better, you know,
Okay.
encoding and the decoding.
But it's a
And-
part of the dimension more tight than the Frobenius norm.
Oh, yeah, sure. Yeah.
Yeah. And
No, but is it equally good then for the intended application, like kernel PCA or something?
so it is
Sorry, kernel SPM.
Cur-
Yeah.
kernel PCA, you mean?
So ultimately, you want to use it for something, right? Representation.
Sure. So yeah, I mean, at least it is as good as kernel PCA in terms of reconstruction.
Got it.
And in the worst case, it could be a factor square root d better than kernel PCA. Okay. Any other questions before I move on to the other thing?
You get the solution of R first, and then factorize it to get A.
Yes.
There are like infinitely many factorizations.
Yeah. Anyone is fine.
Anyway, it's fine. But
Yeah.
for some A, the representation could be sparse or could be bad. Even though the columns of A gives the same space. Some A is better than other A.
It's possible. We, you know, but they all have the same encoding length according to our criteria.
So in this framework, it doesn't matter.
Yeah. Yes, that's true. Yeah.
So you have more general problems you can solve besides just a square, that second, yeah. You set up the byte structure, so this is just an example.
Oh, the degree 2?
Yeah.
You know, there is a kind of a trivial way to extend to a higher degree, right? You can just replace this Vmax as, for example, the top eigenvector of the tensor. But you know, then the you know, at least the problem itself is still well defined, and in terms of the computation, you can somehow, for example, if you have a degree 2R tensor, you just linearize it to degree, like d to the r times d to r matrix. In that sense, we can solve a higher order case. But only in that sense.
You can also only solve the 2, and you can reduce to it.
Yes,
very
yes,
locally
yes,
in the usual
yes,
way.
exactly. Yes, that's all I'm saying. Yes, but it's a next question to study, I think.
If you didn't have error, would it be an easy problem to solve? If you knew that for the examples x, rx squared is the same as x squared, would it be easy? Okay, I guess it would be.
I think that would be, you know, yeah. If you assume that, it will be much easier. Because you can just take a bunch of examples and find the exact, you know, subspace of A.
This relaxation is sort of similar to what people use for, I mean, after this operator norm, it's similar to what people use for matrix sensing. That you have a constraint on the matrix, and you want some linear constraints on the matrix to be satisfied. And the linear constraints.
The matrix sensing. They use
And then what?
operator norm. I'm not sure.
Is it with degree 2 polynomials?
No, I mean, so in matrix sensing, you would think of this rx squared minus x squared as a linear constraint on R. And you would try to find a low-rank matrix that satisfies those linear constraints. Right? And you have many x's. You want to find
Yeah.
a low-rank matrix that satisfies those linear constraints.
But you have equality, right? Rx to the power 2 is equals
So
to.
there usually there's equality, but you know there's also you can say that they also care about the.
You know, when you have equality, which norm, it doesn't matter, right? Like they all give you 0. So.
Yeah, I agree. The norm is equal.
This is not technical, but I wonder, like in applications, do you know the norm that you, everything is with respect to some given norm here, right? Do you usually know the norm that you want to use? You know you want the L2 norm? Like, you're keeping kind of sketches of what you see, but is it, you know, with respect to what?
So I guess you're asking what norm should we use in practice, or whether there's any principle to choose the norm. So usually not exactly. You know, sometimes you have some idea because you say, okay, if the noise is kind of like Gaussian, then it's more, I mean, natural to choose L2 norm because that's the log likelihood, which is the square. And for us, you know, in some sense, for example, it depends on what kind of unsupervised learning task we are facing in the end. For example, if we want to maintain information for any Lipschitz, you know, supervised learning task, Lipschitz with respect to L2 norm, then it makes sense to preserve the L2 norm. And if you want to say, I'm going to encounter, you know, a lot of supervised learning task that is Lipschitz with respect to L1 norm, then maybe you want to choose the dual norm of L1 norm to preserve that norm. So, you know, it's a next question. There's no universal answer, I guess, for this. So, but there are some way to think about it, I guess.
So it depends what you want to do with the data later. You need to decide now how you're going to use the data. You can't somehow remember something about the data that will help you for many applications.
Yes.
In theory, if it's learnable for some norm, it's learnable for all norms, just because they're related by multi-dimension. But in practice, of course, it makes a lot of difference. You want to take the one that's tightest with respect to your classifier later on.
That kind of the sense that in unsupervised learning, you want to learn something that is more general than one specific.
Exactly right. You want a representation that you will be able to reconstruct the original data and learn everything from it. All possible things from it. But that means that the reconstruction error needs to be measured in some norm that will fit your machine that you will learn with later on. That is why the norm is important. If it's a linear machine, that's the thing you said, the linear machine is like a lasso machine going to be later on. You want to preserve probably the L infinity norm. That will make the most sense. So it depends on the machine you will use. But if you don't restrict the machine at all, any norm is good. You know, it doesn't. I mean, basically, in theory, they're all the same up to the dimension.
Okay, so just before finishing this example, so let's have some kind of toy, you know, experiments. This is run by Jeremy Cohen. Yes, and so just to, you know, to demonstrate that this is could be useful potentially. So we are interested in this MNIST classification task where you have a lot of images with digits and you want to classify it into 10 digits. And we use this, maybe I should say unsupervised learning. We do this unsupervised learning using this algebraic manifold idea with data set, a large data set, like 35K images. And after we learn the representation, we are going to solve the supervised task on only a small number of examples, like 170 examples on the left-hand side. And we see that we compare with PCA, the blue one is PCA and the red one is ours. So we get, except the very small case, this is the length of the encoding, the number of components. Except the very small case, we are doing better, but not significantly better. I mean, there are a lot of experimental tricks that could be added on. We didn't do all of them. So, and on the other side, if we use a lot of examples, then we still have something better. But the number of components, as the number of components goes larger, the benefit is smaller. But just some idea about about the experiments.
This tends to say that somehow this polynomial encoding, even though it has more expressive power, it doesn't help you capture images better in some sense?
It does help us a little bit, first of all, and also there are kind of other things hidden here. So, for example, because we, according to our theory, we lose something in the length of the encoding. So, we want to shoot for encoding of length k, and using a theory, we only have encoding k to the 4 over epsilon to the 4. In practice now, that's a big deal. K is 5 versus something. So what we did actually is that we use some kind of non-convex heuristic to solve this algebraic manifold problem. So which may not really, really works to really get a global minima. We just convert some local minima, and that's probably another reason why this doesn't work that well as we expect.
You can say what's the y-axis for classification accuracy?
This is the classification
I've
accuracy.
seen this before with,
This is classification accuracy.
So you reconstruct and then do what?
Oh, you don't reconstruct.
Okay.
So you map the data to the representation. Like this is the length of the representation. Which, for example, let's choose it to be 10. So every data map is mapped to dimension 10, and then we use this as the feature, or we pretend this is the new input, and we learn a mapping from this 10 dimension to the label, and we measure the classification accuracy.
This is a linear classifier on
the 10 dimension.
Is this something synthetic, so you know what's the right solution, or?
This is real data, MNIST.
the digits.
Yeah.
Okay.
This is sort of how much. So the reconstruction is would be perfect in this case. I mean, with your parameters or no?
No, I won't.
It would not be perfect.
Yeah.
And so you're representing it with with 10 numbers, the image.
Yes.
And just the argument is that the representation you want to learn has to be good on future supervised learning tasks. So that is what we're measuring. That's all.
No. The reconstruction is something different, right?
No, the reconstruction is what guarantees that you could classify as good as the original data. That guarantees it. You never actually need to reconstruct. You will just need it for the training of the compression.
Okay. So now let's move on to the improper diction learning. So.
And actually, one more question. So
Sure.
if you have just a neural net with 10 hidden units,
Okay.
which would be the analog, right?
Yes.
You would get like 95. Or
Yes.
90.
Definitely.
With 10,
Sorry. With
Yes.
10. Oh no. With 10. Maybe I think it should be above 90, but maybe not as good as 99 something.
No, 99. I mean 95.
But I'm just saying that the 10 digits, 10 hidden units it's very different from 100 or
I thought
200.
even 10 do pretty well, right?
Like 90, but for MNIST, like 90 is a big difference from 95.
I know.
Yeah.
Yeah, but it would do much better than PCA.
Sure, that's true. But we are doing it with only 170 examples.
It says 35K images. I don't know.
That's to train the representation. So for the unsupervised learning part, we only have 35,000 images.
170 examples. I see, because you're in the representation learning.
So it's like 17 examples in each class. There are 10 classes in this.
So I don't know what the numbers would be.
Yeah. Okay, so now let's move on to the diction learning. So in diction learning, what we want to do is that we have some data X, and there's a dictionary. This is like a very wide matrix. We have all of these columns as a basis, and we want to represent our data as a sparse combination of the bases, the columns of the matrix A. And so Y is often referred as a sparse representation, A is referred to as a dictionary. Okay, so the existing approach either use alternating minimization heuristic, or assumes some generative models and structures about the dictionary. So like in theory, we have this works by Spielman et al. And with Sanjeev and Rongo and Moitra, and also David had works on this. So often we assume generative models for the dictionary. So we assume that X is really generated from A times Y plus some noise. And also there's assumptions on Y, assumptions on A. And in this paper, we are going to do a discriminative version without these assumptions. And also we have to do it in an improper way, which I'm going to talk about. So so what is the encoding? So the encoding is that we want to find the best representation Y. So given X and given A, we just try to find the best representation Y. We replace the L0 sparsity by L1 sparsity. So just to use it as a surrogate. And then in the decoding, we multiply just A back and reconstruct the original data. So this is the encoding and decoding class hypothesis class. And we also assume that the dictionary has a L infinity norm less than 1. By this, I just mean that the largest entry in this dictionary is less than 1. So this is just some normalization constraint. And our framework, the error is measured as the expected reconstruction error, right? So we have encoding HA of X and decoding GA of the encoding, and we measure the reconstruction in L1 norm. In this case, is we can also do it in L2 norm. It's just a little bit, theoretically convenient to do L1 norm. So, and we can replace all of these definitions together into this formula, and we are going to get such a formula. So minimum over A and expectation of the minimum over Y of X minus AY, the 1 norm. So I guess from this you can see why this is kind of difficult to optimize it exactly, because first of all, to really do it, you have to replace this expectation by the empirical expectation, the empirical samples. And we have A and Y both as variables. Actually, if you replace this expectation by empirical things, you are going to have multiple Y's for every example. So that's why we face a non-convex optimization problem. And our goal here is a little bit weaker compared to solving exactly this optimization problem. We are going to just output an encoder and decoder that has comparable error compared to epsilon star.
So if you're bounding the L1 norm, why would this be a compression in general? Or is this just a relaxation for the 0 norm?
Yeah, I mean, this is so we are okay, let's put it this way. So we can replace this by 0 norm, and we can compare it with that. I mean, comparing with this is just a stronger requirement. If you can do as well as the L1 norm thing, you can also do as well as the L0 norm thing. So I mean, I guess
the question was, why is it a compression?
In terms of the definition of the error, this is okay. You agree with that? And in terms of compression, we are going to have algorithm that just have explicitly compression. We are not going to output a vector with L1 norm less than something. We are going to really output a sparse vector. But this is a way to compare the error. So we are comparing the error against some stronger thing. So that's okay.
Actually, you can always output the L1 bounded vector and then you can sample from it. And you can sample from it log n times L1 norm, and then it's the same as the L0. So the L1 and L0 norm are up to log factor close, almost always.
Okay, so here is our convex relaxation based approach. So we are going to, for this purpose of this talk, we are going to only do this group decoding, where we take a group of examples and we compress all of them, and then we are going to do a group decoding that decode all of them. So with a little bit more trick, you can do it for one example. But in this talk, we're going to talk about the group case. So we have this data X, which is a D times n dimensional matrix. So you can think of it as just the n different data points that you put them as the columns of capital X. And recall that the kind of the scenario that we're thinking is that, roughly speaking, a data point is roughly something like A star times Y star. Think of A star and Y star as the optimal one. And the capital I is something like a capital A star times Y star, where Y star is just have columns of the representation. So our encoding consists of two steps. The first one is a denoising step, where we want to find the matrix C, which is close to X, and the C is in some convex set K. So in some sense, the intended solution of this optimization is that Z is A star Y star, and K is going to be designed as a set that contains all of the matrices C, such that C is representable as A times Y. Of course, A and Y satisfies those constraints, like A has infinity norm less than 1, Y has sparsity less than K, so on and so forth. So in some sense, this first step is trying to remove all of the noise in this approximation and get A star times Y star. Of course, we cannot do that exactly, but we're going to talk about that. And the second step is that we're going to random sample this matrix C, which is a D times n matrix, and we sample a few entries in each column, and that's our representation. So that's why it's a compression, because we really explicitly sample this matrix and make it low dimension.
Wait, so Z is an approximation to what? X is that? Oh,
X is our data.
so sampling is on our denoised version of A times Y.
Yes. Oh, sorry. Denoised version of X. A times Y is already. If you get A times Y, you got already denoised.
Yeah. Okay. Sorry. Our guess for A times Y.
Yes. Yes.
So I will never learn what the dictionary is in this process.
Right.
I will only learn some closest representation of X that could be obtained by dictionary potential.
Yeah. We only learn a representation that is comparable to the best dictionary.
You have no choice because the dictionary learning is NP hard.
Great.
There is no way you can compute the dictionary. But what they did is make all these assumptions to allow it.
Can you implement something in place of Z? I mean, it's supposed. Okay. I mean, what? I mean, Z is not supposed to be a sparse guide in that case, right? Because if you would sample entries of Z, that would be.
Z is A times Y. A times the sparse guy.
Yes, yeah, but I mean, if it would happen to be a sparse guide, that would be bad for the sampling, right? Because,
That would be bad, sure, but it won't be. I think it won't be a sparse guy because you make you know, I mean, if it's sparse, then I think the problem is kind of like a relative trivial, so it's still okay.
You don't need a sample if it's sparse.
So I don't understand this. So in dictionary learning, I mean, if suppose you assume the data is actually from a dictionary learning model, right? So the assumptions are true.
So they're exactly true.
So then you're saying that, right?
Yeah.
Then you don't need to compute Y at all. You're given Y,
Yes.
right?
I'm just going to sample it.
Not even sample, right? It is sample for you. Let's say it's a dictionary learning with sampling. Yeah. So that cannot. Why should that be a good representation? It doesn't. Right. Suppose data was actually from a dictionary, right?
Mm-hmm. So exactly.
A times Y, and sampling you can do, or maybe nature does it.
that
should not be a good representation.
No, why not? It's a sparse representation.
Yes.
Why is there sparse?
We're going to sample this matrix Z.
But nature could sample.
Interesting.
Nature.
So let's say you're saying the image is from the dictionary, right? And now it's actually from the model.
Okay.
So sampling, nature could do the sampling, right? It could give you some pixels. And somehow you're saying that's a good.
Yeah, that's what I'm saying. Because you can recover the original image from it, and it's sparse. And therefore you can do any supervised learning task on it later on. And that's what you want. If you agree that this is what you want for a month.
Yeah, no.
Yeah.
But
I know you don't agree. You think of other things you want to do with it. But if all you care about is supervised learning, this is all you need.
Just to clarify, you choose omega to be a random subset?
Yes, a random subset. A random subset. Yeah.
It seems like it might be better to choose it according to the entries of Z, that is like the large entries.
Yeah, we are ignoring that kind of thing.
Yeah,
You're ignoring it, so if
Sorry,
if it was sparse, then you would get zeros going in your sum.
Yes, I mean, but if it's sparse, I think
You would never be sparse.
Z.
When you measure errors somehow it
Yes, when you measure the error, it's okay. Yes, that's exactly.
the most sparse guys always have small norm.
So basically, if it's sparse, then basically output 0 is already a good answer.
Zero is a wonderful representation of this thing.
So just to understand, the image that you get here will not be sparse or whatever, but somehow compression has happened because it is produced by some simple model.
Mhm.
Is that the reason this is a compression?
The image is not sparse, but the reason you can compress is that it comes from some model which with the sparse representation.
Yes, this is exactly true. Yes.
Okay. The decoding is just we are going to find. In sometimes we are trying to find Z. That's the only thing we want to do, because if we can find Z, then we have already. I mean, we have already done as good as the best dictionary. And what we do is that we just find the decoding C with the variable C here again, and that's so that the random sample version of the C is the same as Y.
So that means that you're trying to put zeros, but it doesn't mean you're trying to put zeros in the positions of Y that you can sample?
No, this is P omega of C.
Yeah.
So the intended solution is that you just put Z here, which is perfect.
The norm only takes the coordinates in omega, I think?
Yes.
Okay, I mean, that's not really.
Oh no, this is a sparse matrix, P omega of C, and Y is also a sparse matrix. I mean, on all of the entries that are not in omega, they are 0.
If Y has a non-zero entry in something that's not in omega, does it?
Y cannot be that, right? Y is our sampled version.
No, but in the reconstruction. Right?
Yeah, this is the same Y.
Okay, so, sorry. Okay, sorry.
You encode and you get sparse thing, and then you use the same Y.
Why is it?
You don't get new examples and then decode. You don't do the decoder for new examples, right? In this setting.
Yes, for this slide, yes, we can do that, but here we only do the simple thing.
You can do it with this scheme or?
Not exactly the scheme, but with some variance. Yes. Okay, so let's just talk a little bit more about how to analyze this. So why this can work. So first of all, we have mentioned that K is designed to contain all of the the matrices that can be represented as A times Y, and also we want the complexity of K to be not that large, because if K is everything, then this minimization problem will just give you the original data, because that's the best thing to do with error 0, and then if you do this random sampling, it will be like problematic. So basically, we want that this convex set K, we want it to contain all of the AYs, but we don't want to contain too many more things. And also, it is known that if this random marker width of this set K is, let's say, W, then I'm going to define the random marker width in a moment. Then we can sample just W entries from Z, and that allows us to reconstruct the matrix. So the basic idea is that you have some matrix with low complexity under this random marker width kind of measurement. Then if you sample it, you can reconstruct from the sampling. Okay, so that means that basically there are three things that we need to do. So one is that we need to define a convex relaxation, and the second thing is that we want to prove that the convex relaxation has a good random marker width, which I'm going to define it for you. And then we want to have an efficient optimizer for this convex set. And if we can do all of these three things, we can say diction learning can be learned improperly, discriminatively, with encoding length k squared times r to the 1 over p over epsilon squared, where k is the desired sparsity. We lose a factor squared there, and r is the over completeness of the size of the basis. So usually r is something large. That's the over complete case, which is often challenging. And our dependency on r is 1 over p. P is a constant that you can choose. It's the kind of like the degree of the sum of squares relaxation. And the runtime is O of d to the O of p squared. Okay, so this is our main theorem, and we are going to do sum of squares relaxation. And the first step is basically by definition. With a little bit trick, you need to change these norms into the polynomials. And the main point is the second one, how to bound the random marker complexity. And the third one is also by definition, because we can optimize sum of squares relaxation. Okay, so next let's talk about the relaxation. So this is our set Kstar, which is the smallest one, which could be non-convex. And we want to find in sum of squares relaxation, we can find a sequence of tighter and tighter relaxation like this. The larger the index, the tighter the relaxation, and the smaller the random marker width. And the smaller the random marker width, the better the encoding length. Okay, so let me just briefly introduce some of squares convex relaxations for our setting. So often we have the setting that we have, let's still call it Kstar is a solution of a polynomial equations, Q1 up to Qn. So they are the roots of these equations. And sum of squares relaxation can do for us is that we can have the sequence of relaxation with the following property. If there exists a subsort proof for the statement, let's say b minus a dot x, this is a linear inequality. And if we have a proof for this in the sense that this guy is representable as a sum of squares of the polynomials plus a sum of multiples of qi's, then so there are some constraints on this, right? The degree of all of these cannot be too large, so that we can efficiently optimize them. Then we can say that for all x in this set k sub p, the inequality is indeed true. So recall that k sub p is a larger set. So and in Kstar, this inequality is definitely true. But here we can say also in the larger set this inequality is true. So just summarize this in a line. I guess this says that the linear inequality provable by sum of squares are preserved by the relaxation. Okay, so and now let's see how do we do it for our case. So what we are going to do is first we want to rewrite this constraint set as polynomial equations. That's what sum of squares will do. So before we have this kind of constraints, and now we relax it to we replace the norm of a infinite norm of a less than 1 by aij square is less than 1, and we first rewrite this one norm as p over p minus 1 norm. You see a moment why we want to do this, and then I'm going to replace yij by some wij to the power p minus 1. Then before this is not a polynomial, but now it becomes a polynomial. That's all I'm doing. So I'm just raise it to the power p and make it a polynomial. And then I'm going to do the generic sum of squares relaxation to get a degree p's sum of squares relaxation. Okay, and now let's define this random marker width, which is of the convex set. So we first take an arbitrary matrix in this set, or actually vector in this set, and we linear product this vector with the p omega of a random +1 -1 variable. P omega is the random sampling of the +1 variable, and we take sup over this, and then we take expectation over the random variable Kstar, which is +1 -1. The exact definition doesn't really matter too much for us. So what really matters is that this is
an eta from a. Oh no, the matrix is random. I see. It's not a random low rank matrix.
Which one? Which letter?
Eta is itself a matrix. I see.
The Kstar?
Yes, sorry.
Kstar is a random binary matrix. And also omega, or maybe I should also take expectation over omega. So omega is a random sampling. So this is one reasonable way to measure the complexity of this set K. If you are not familiar with that, it's not going to be a big deal. The only thing we want to do with this, so you want to say this quantity is small, right? If this quantity is small, then it ensures that you can recover from sampling. And basically, what we want to say is for all C in this convex set, C times the p omega of Kstar is less than something, less than the random marker complex width. So the important thing is this is a linear inequality over C, and we want to establish for all points in Kp. And recall that we have said linear inequalities provable by sum of squares are preserved by this relaxation. That means that we only need to prove this linear inequality by sum of squares proof, and that's what we are going to do. I'm not going to show the proof for you, but basically the way that I cover is just you start with first with a not sum of squares proof, and then try to make every step sum of squares by using Cauchy-Schwarz, other tricks. And this will lead us to the statement that the random marker complexity of this is less than this quantity, p square n k square r to the 2 over p. So basically this just means that recall that we have a d times n matrix, and we have said that you only need this number of entries to recover the whole matrix, and we have n columns, so that's why every column we only need k squared times r to the 2 over p entries. So that's how we get the encoding length, k squared times r to the 2 over p. Okay, just wrap up. We have talked about these two problems, and just recall that this is our original motivation, and we want to remove this two line. So by introducing a definition so that we can evaluate a potential solution with quantitative objective quantities, and the structure is evaluated by the succinctness and how little information it loses in terms of the reconstruction error on the test data. I guess I'll stop here. Thanks.
So from a coding theory point of view, what you try to do here, you have lossy compression with respect to some norm, I guess, and distribution, right? You have a norm. So the norm is known, the distribution is not known.
It's more or less known because you can sample from it.
Okay,
Yeah,
so you
yeah.
can only, so you can learn the distribution and then construct the code, right?
The distribution could be quite complicated.
So it's so this is the thing. You're not decoupling this to like.
Yeah, we don't want to decouple this.
So you want something more efficient than just learning the distribution and then constructing. You want to construct the lossy codes online somehow with the samples.
If I can say so, I mean, generally, if you want to encode something, you cannot distinguish a random string of bits from a string that is very compressible. This is incomputable, right? And one-way function and all this kind of thing.
Okay.
The only way you can get around, and many of these problems that NP-hard they suffer from the same difficulty. The only way you can get around it is by saying I restrict myself to a set of encoding procedure. And then I compare myself to this set. And I don't even need to find the compressor from within the set. I find compressor from outside the set that will be as good as from the set. It's called improper learning, and it's very powerful thing to do.
So okay, so you have lossy coding with distribution and norm, but you only allow the procedure, the F and G to be from a specific set. Still,
Compared to them.
Compared to them.
Yes, because maybe within them it's also NP-hard. Like
Fine,
this,
but
for example,
why don't you just learn the distribution and then find your GNF? This is just
no, the whole distribution is kind of is not important. It's, I mean, this is just a public generalization. It takes large enough sample, you will have generalization error. So you can think of it as even deterministic. It doesn't have to be the distribution thing. Take enough samples. Now you want.
Oh, you just want efficiency. You're claiming that you just want to do it efficient. To find F and the G.
Okay, there are two different
So
efficiencies.
there's sample
Samples,
efficiency
yes,
and
right. So when you construct an encoder, you want to make sure it's from a class that is, first of all, efficient computationally to optimize over. Second, not too large. You don't want from all possible encoders. The sample complexity will be too large. So it has to be relaxation to the original hypothesis class, but not too loose. This is the picture that Tengyu drew on the...
So the distribution, learning the distribution is not the thing, the thing is computing the F and G efficiently?
Yes. So the distribution learning, I guess short answer is that learning a distribution usually is often even harder because you have a high-dimensional distribution. They could be on some manifold. All this manifold learning, are not quite efficient. So learning a distribution, or at least you just really learn that distribution exactly. Usually is not a quite promising idea. There could be other ways to learn the distribution, but it's not. We don't want to do that.
I think our point is that if the distribution is so simple,
if the distribution is so simple.
Yeah, if distribution is simple, then you have no problem. You could
Well,
just compute that.
It's not easy papers, but yeah.
No, I don't know.
Yeah, so that's pretty.
You can do previous
I mean, but it's not, intractable.
So the thing is that the distribution is general here?
And also, sometimes you don't know what the form of the distribution, right? You can only learn it when you have a parametric form,
Okay, they're assuming there's no distribution. Allah doesn't like distribution. So there's like this, that's all.
I like this.
So can you
not assume anything about
right. Yeah.
So it's like a more general. That's what's confusing me.
Yeah. So what Sanjeev is referring to is that you assume the distribution is generated from something. You have a succinct parametric form, and then
or maybe not even, but yeah, something. There is some form. Yeah.
Yeah. So there could be a problem with this, which is that if the data is not from the distribution, that's one potential benefit of doing it without assuming the distribution has some special form, because you might have model mismatch.
You need a distribution just to measure yourself, your notion.
Yes.
Then you
Yes.
measure yourself on a label,
Yes.
on a supervised task.
Yes.
Right?
Yes.
So the distribution has to be there anyway.
No, just
Yes.
I think these are two
You
different...
can always
That's
assume
it.
it's I. You cannot.
That's it.
It does, it's from the distribution that generated the data.
Yeah, it has to be there in the definition. Sure. Yes.
So it has to be.
Yeah. This is whether one to.
So one distribution, what we discussed is the path distribution of the data. That to do with two, that exists here too.
Yeah.
But if you want to
I
learn
was
this...
making it clear.
No, but I think, but they talked about another distribution. So if there is you want to learn this NP-hard dictionary learning problem, what people assume is that there is a distribution over the dictionary.
The generative model.
That doesn't exist yet.
So I have a question. So suppose the family of decoders are simply those that leave just a small subset of data, a constant number of samples.
Uh-huh.
That's like we use in supervised learning with this notion of compression. You look at all the data, you remember only a subset of them, maybe some notes for yourself, and then you are allowing to. That's what you are allowed to do. Can you
Just subset of samples.
Yeah, like they do in the supervised case. This is a well-known notion of compression, and it's equivalent to having finite DC dimension.
Yeah, we have to prove generalization bound, we use exactly the same machinery.
Yeah, but
Yes.
if you don't have the labels, does it make sense just as a class of compressors, of encoders and decoders? Just pick a subset of data. Can you do anything with it?
I mean, that's the computational problem, right? So if you,
Yeah.
yeah,
I mean, you gave 2 examples. I'm suggesting a third one.
I think it essentially, I think you will run into computational kind of problems. I think essentially it might be okay to do it, like in terms of generalization error bounds. But efficient computation, you might be, how do you reconstruct, right, in your example?
I guess like this is, I guess what you are saying is indeed what we are doing. So we have a set of training examples, and we want to minimize this reconstruction error, and with the constraint that the compression is good, and we just do it for the training example. And because we have enough training examples using the VC dimension type of bound, we can say that okay, it will also work for the future unseen examples, the test examples. That's the same rationale, like the same philosophy. Yeah. Any other questions?
Thank you.